Welcome back to Die Hard American Metal. Today, we are going way beyond the basics and diving deep into the real engineering of precision. We're talking about advanced die design. This isn't just about raw power. It's about the incredible science that truly drives modern American manufacturing.
So what really is the difference between brute force and precision engineering? Well, think of it this way. It's the difference between a sledgehammer and a surgeon's scalpel. And what's wild is that in the world of metal stamping, a die has to be both. It's the science of applying thousands of tons of force, but with microscopic precision, to cut and shape steel as if it were clay.
Okay, here's our roadmap for today. We'll kick things off with the physics of a cut, then get into the secret of clearance. After that, we'll crunch some numbers for blanking tonnage and the math behind bending. And we'll wrap it all up with a look at some advanced shaping operations. Let's get into it.
All right, Section 1, the physics of a cut. Or, as I like to think of it, how metal truly breaks. Look, to really master die design, you have to understand what's happening on a microscopic level the very instant that punch makes contact with the metal. And trust me, it's probably not what you're thinking.
You know, a common misconception is that we're simply cutting the metal, kind of like scissors through paper. But that's not it at all. What we're actually doing is initiating a controlled fracture. As the punch penetrates, it creates this intense tension and compression, which causes the metal to deform. Then, and this is the amazing part, tiny cracks start to form at the sharp corners of both the punch and the die. With a perfectly designed tool, these cracks actually race toward each other and meet right in the middle, shearing the part off cleanly. It's a beautiful, violent little sequence that we can predict and absolutely master.
Every single sheared edge tells a story. Seriously, if you pick up any stamped part and look closely at the edge, you'll see these two distinct zones. There's the burnished band, that's the smooth, shiny part where the punch and die did their job. Then you've got the break-off, which is the rougher part where the final fracture happened. For a die maker, the size and the quality of these zones, well, that tells them everything they need to know about the health of their tools and the precision of their setup.
So that leads to the big question, right? How do we control that perfect fracture? It all comes down to what is arguably the single most critical variable in all of die design: clearance. That tiny, precise gap between the punch and the die.
And man, this slide right here illustrates the razor's edge that designers walk every day. If your clearance is too tight, those two cracks we were just talking about, they won't meet up. You end up just mashing the metal, creating a secondary shear that wears out tools like crazy and demands way more force. But on the flip side, if the clearance is too loose, you're not really shearing anymore. You're just tearing the metal, which leaves a big, ugly, sharp burr on the part. It's all about finding that perfect sweet spot.
So how do we find that sweet spot? Well, engineers don't guess, that's for sure. They use proven constants like these to calculate the perfect clearance. And as you can see, it completely depends on the material. Softer stuff like aluminum uses a totally different constant than hard steel. This value is absolutely critical for the formula that ensures a perfect cut. It's really fundamental to quality stamping.
Now that we understand how to get that clean cut, the next question is pretty obvious. How much force does it actually take? And this isn't just some academic question. The answer determines the kind of machine you need for the job. Knowing this number is critical. I mean, if you underestimate the tonnage, you could damage the die, or even worse, the press itself. If you wildly overestimate it, you're just being inefficient, using a massive machine for a small job. Precision is absolutely key. The answer lies in this simple but incredibly powerful formula. This right here lets us calculate the exact force required just by accounting for the part shape and the metal's own properties.
Let's break this down. The force, F, equals the total length of the cut's perimeter, that's L, times the material's thickness, T, times its shear strength, S, which is a known property of the metal. You just multiply those three together, and you have your required cutting force in tons. Simple as that.
But, of course, the real world is never a perfect textbook example, is it? So we always add a safety factor of somewhere between 15 to 30%. This is to account for variables like the tool getting a little dull over a long production run or slight variations in the material's thickness. It just ensures the press can always get the job done, no matter what. Okay, let's move beyond just cutting and talk about another critical operation: bending. And just like with cutting, there's a precise science to predicting exactly how a flat piece of metal is going to behave when you fold it. When we bend metal, it's not a simple fold. The metal on the outside of the bend has to stretch, while the metal on the inside gets compressed. But somewhere in the middle, there's an imaginary plane called the neutral axis, where the material stays its original length. The whole secret to a perfect bend is calculating the exact length of that arc along the neutral axis.
And you guessed it, there's a formula for that too. This one lets us calculate the bend allowance, the precise length of material needed for the bend itself. It looks a bit complex, but basically we take the bend angle, A, and multiply it by the sum of the inside radius plus this thing called a K-factor times the material thickness. This gives us the exact length we need to add to our flat pattern to get a perfect final part.
So what is that K-factor? Well, it helps us pinpoint where that neutral axis is located, and it all depends on the sharpness of the bend. There are really complex tables for this, but a great rule of thumb is what you see here. For a sharp bend, the neutral axis is about 1/3 of the way into the material from the inside. As the bend gets gentler, it moves closer to the center. Getting this location right is absolutely crucial for an accurate bend.
All right, finally, let's look at two advanced operations that really build on these principles: forming and coining. They may sound similar, but they shape metal in fundamentally different ways.
The difference is all about how the metal is being treated. Forming is basically an extension of bending. You're stretching and shaping the metal into a new geometry. But coining is a whole different animal. You apply such extreme pressure that the metal actually flows like a thick liquid, filling every tiny detail of the punch and die. It's how you get those razor-sharp details you see on, well, coins.
And you know, all these processes, cutting, bending, forming, coining, they're all governed by this one elegant principle of plastic deformation. You can change the shape of the metal, you can move it around, but you can't create or destroy it. The volume you start with is the volume you end with.
Period.
Understanding these calculations, these forces, and these principles, that's what separates an operator from a true master of metal fabrication. This is the engineering that powers modern manufacturing. So now that you know the science behind the force, what will you build with it?